Hey everyone, once again, welcome to the Simulation Night School. This is Damon Tordini, Simulation Application Specialist at Hawker Systems. We're going to be continuing the content that we started on Tuesday of this week with the second half of our presentation focusing on stress analysis and fluid analysis in SOLIDWORKS Simulation. The agenda for today is to pick up where we left off on Tuesday, where we were running that stress analysis on the pressurized tank system on the back of a truck frame, where we had just finished setting up all of the conditions and we had gotten some results that we were starting to review. And so what we're going to talk about in part two is how we can do a little more investigative work to check those results and make sure that they're a valid result, make sure that we're getting good data out of our simulation. And we'll talk about this concept called convergence. We're also going to talk about how to make sure the results you're seeing match real world or something else that you might be comparing them to where you're trying to gauge the accuracy of your simulation. And then the second half of the hour we'll be talking about SOLIDWORKS Flow Simulation, which is the computational fluid dynamics analysis tool inside SOLIDWORKS. And we'll cover most of the same topics we've covered for the stress analysis, from how to set up a typical problem and the basic workflows, common things you want to watch out for, little tips, and of course how to sort of view and validate the results at the end. So let's start by talking about results convergence. So many of you may be aware that in a stress analysis, whether we're talking about SOLIDWORKS simulation or any other simulation program, the quality of the results you're going to get from the program is directly dependent on the quality of the mesh. You should never assume if you've run a stress analysis that the results you're seeing are correct or quote-unquote the right answer until you've proved to yourself that the mesh you've used for that analysis is adequate, is a good mesh. And you do this by proving that the results are what we call converged. A lot of times people don't exactly know what that term means, convergence, and specifically what we're referring to there is the process where when we create a mesh and we're doing what we call discretization to the original geometry that we've created in SOLIDWORKS or imported from another program, convergence is basically the process of making that discretization, where we're breaking the model up into those pieces, more and more accurate. So basically, the smaller the pieces are and the more of them we have, the more accurately we're going to be able to match the original geometry. And as we approach the true shape of that original geometry, we are, of course, experiencing convergence. So the convergence is just the process of reducing the error in your simulation due to the mesh, because we're mapping that real geometry better than we were. So how do you check for convergence, and how do you know that you've achieved convergence? Well, there's three main methods for doing this. The first method is probably the method that all of you have done at least at some point, maybe not intentionally, and that's just manual inspection. Basically running an analysis and looking at the results, and then seeing if you run the analysis again with some other mesh settings, if there's a difference in the results. One tool that can help you with that is called the trend tracker, which will make it easier to see what the results of, for example, stress was at the last time you ran a simulation. Other ways you can automate this a little better is by using the design study, where if you set up a simulation, you'll be able to run it in a batch multiple times with different settings for different input parameters. So for example, a slightly different value for the global mesh size. Or you'd also be able to use something called the adaptive meshing, which is a built-in algorithm that will try to automatically create the best possible mesh you could get to achieve accuracy in your simulation. So just to dig a bit deeper here, again, the manual inspection method would really be basically to run an analysis and then go back and increase the mesh density either by putting mesh controls in or just by globally refining the mesh, and then run the analysis again and review those key results, so whatever the important results of your analysis is, like the maximum stress, for example, and you basically repeat that process until you don't see those results changing significantly anymore. And the user, you yourselves, will have to decide, what the definition of significant is. What is an acceptable amount of change as you're changing the mesh and running these analyses? If you see the maximum stress go up, but it's only 0.5%, maybe that's within your tolerance, and you decide that you've achieved an acceptable level of convergence. If you want a more automated method, that's where the adaptive meshing tools can come in handy. And these adaptive meshing tools are basically two different algorithms, two different methods for how the mesh can be automatically refined. Now, the main benefit of these methods is that rather than requiring you, the user, to define a mesh control or select exactly where you want the mesh to be refined, these adaptive mesh tools will automatically refine the mesh anywhere that it needs to be without you having any direct input. And it's only going to be based on the error in the mesh. So it's basically automatically optimizing the mesh so that you have all the detail where you need it and not any unnecessary refinement. So the two main methods here are the H method and the P method. Basically, the difference between them being that the H method will add more elements, more and smaller elements, very similar to if you just put a mesh control on and refine the mesh again. And so, of course, the number of nodes and number of elements would increase if you use this H adaptive mesh. And then there's another method called the PIAT Activity method, which instead of adding more elements, essentially will increase what we call the order of the elements by adding more nodes inside the element, and that makes each of them more accurate and more capable to adapt to the original geometry as well as the deformed shape of the model. So it basically is turning those elements into more advanced versions, similar to how you have a draft quality element that can then, of course, be set to high quality instead, which has greater accuracy. And typically we see the H adaptive method used more often, probably because it's easier to see clearly from the visual feedback in the software how this adaptive mesh is working. And there are, of course, a lot of options you would be able to tweak as far as what level of accuracy you're looking for and so on and so forth. But at a certain point, you would look for the stress levels in any of these methods to essentially level off, again, as the graph back here shows. Now, there may be one instance that you'll encounter from time to time where you won't see the stresses level off in this way. Instead, you may see the stresses basically increase to infinity, going higher and higher no matter what you do to refine the mesh. And of course, you won't see a convergence if you experience that. That situation is a peculiar case of a stress concentration called a singularity. We've all probably seen stress concentrations before. Those are just areas of high stress in a model, and typically it's the area where we're going to experience a failure in whatever product we're designing. So it's usually the area of concern. But there are certain situations where this concentration of stresses displays unrealistically high stress values. So it is the area of the model where the highest stresses are, but the actual number isn't realistic. And this is caused by the fact that stress sometimes occurs, the highest stress sometimes occurs in these sharp corners of a model. And just due to the nature of FEA calculations, it's basically not feasible to get a stress measurement on a sharp edge or sharp corner like this. So in those cases, if you're trying to use the maximum stress to check whether you've achieved this convergence of your results, you won't be able to get that. And again, you can determine whether or not you have a singularity just by remembering these basic rules. If you don't have any kind of sharp corner or what we call a geometrical discontinuity, then it's not going to be a singularity. But if that does exist, it most likely is a singularity. Again, if you are trying to converge your results by refining the mesh and rerunning it, if you start to see those stress values level off, then you don't have a singularity issue. But if they don't converge and the stresses just keep going higher and higher, that means you do in fact have a singularity. And of course, in that case, you cannot trust the stress values. So the solution in these cases to the singularity problem is, if you can positively identify one and you have verified that it is in fact a singularity that's not giving you a good result, you can either choose to just measure some stress values in the vicinity of that corner, for example, 1 or 2 elements away, or you could also go back and modify the model to get rid of the corner and instead put some sort of a fillet or other blend to have a smooth transition between the walls, just like the image in the top right corner there. And in that case, of course, when you've eliminated that sharp edge, the singularity phenomenon will go away, and you will once again be able to get proper convergence of your results, and you'll be able to see what that maximum stress is. If you'd like more information about these adaptive methods or the convergence process in general, I would recommend going to the support forums on the Hawkridge Systems website, which is at support.hawkridgesys.com/forums. You can search for this convergence document. It's called Achieving Convergence in SOLIDWORKS Simulation. It goes into more of the background theory and how exactly these methods work. And of course, we have a large number of other technical documents and just help files and typical discussion forums on a variety of both SOLIDWORKS topics and simulation topics. So go ahead and check that out when you get a chance. Now, assuming that you are able to check convergence and you're pretty sure you've achieved a good result in your simulation, at least as far as the mesh is concerned, you may also be trying to check the results of your simulation versus something else that you have done before, maybe a real-world experiment, or maybe some guidelines that you've been given, or a standard, or something like that. And you might be trying to judge whether the simulation you ran was accurate by comparing it to these other things. So when you want to match your simulation to real-life results, there are a number of things you should try to keep in mind when you're trying to figure out if the problem of some sort of a discrepancy is due to perhaps the software, or if perhaps it's because instead the conditions that you're using maybe aren't the same as what you're comparing your results to. So the first question you should always ask yourself if you're trying to compare the results of a simulation to something else is, what exactly are you comparing them to? Are you comparing these simulation results to a hand calculation that predicted the result of the FEA analysis that you did? Are you comparing it to an experimental result, a physical test that someone did on the real product after it was manufactured, which may have different conditions? Are you comparing it to some other program? Was it the same kind of analysis program, or was it checking for something else? Or was there a difference in the way the program approached the problem? All of these things are really important questions to ask when you're trying to decide which answer is the right answer and which answer is the wrong answer. For example, if it's a hand calculation that you were trying to compare the simulation results of, let's say, a deflection of a beam, you may have a hand calculation that you tried to run where you plugged in the equation that you found in a table somewhere of what the deflection of a cantilever beam is, and maybe you got a very accurate result. Of course, you didn't have to do any kind of meshing or anything because it's all hand calculation, which was derived from some sort of integral. But most likely the geometry of whatever you're trying to run your analysis on in the software is not exactly the same as whatever that equation was derived for. It's probably not a simple cantilevered beam, fixed at one end with exactly the same length and section properties and all those assumptions. Remember, that's really the reason that FEA was invented in the first place, so that we had another method to evaluate the real geometry of products rather than trying to assume that they're just an idealized shape. So here's an example that we actually saw recently in dealings with a customer. We had a customer who designed liquid storage tanks that had previously used a hand calculation to try to figure out what the deflection of that tank was under pressure. So they had a formula that they, of course, obtained from a text that was sort of their standard guideline that they used for a long time, where they had just assumed that the wall of the tank was a simply supported plate, which means that it's just basically hinged on the sides and the bottom, and it's free to move on the top. So they had their hand calculations done for all these products, and the formula that they had gone off of was predicting a deflection at the top of the plate of just under ½ an inch, about 0.485. And the reason they originally came to us was that after they had run this hand calculation, they then tried to set up a simulation in SOLIDWORKS where they figured by doing a stress analysis, they could validate the software by making sure it matched the hand calculation. So they modeled up the tank, and they set up their stress analysis. They put the right material properties in, and they fixed the bottom of the tank and put the same pressure load on the tank, which in this case was a non-uniform pressure to account for the gravity effects and the greater pressure at the bottom of the tank. But when they ran the analysis, they found that the displacement in this wall of the tank was a lot less than the formula predicted. Their formula predicted almost ½ an inch, but SOLIDWORKS Simulation was saying about 0.19 inches. So their initial thought was, well, there must be something wrong with the simulation. Maybe there's a problem with the program. And of course, once we looked into it a little further, what we realized was their hand calculation was assuming just one wall of the tank needed to be analyzed, and it was assuming that those edges could be hinged. And so we thought, well, we better run that simulation exactly in the software. So we went ahead and, of course, simplified the model down to just one plate and used the exact same conditions as the hand calculation. So put this immovable constraint on those sides and the bottom of the tank and put the same pressure load in. And when we ran this analysis and we looked at the displacement, turns out that the result was the same as the hand calculation, about 0.479 inches here. So very, very small amount of error compared to that hand calculation. And so it turned out that there wasn't a problem with the software or a problem with the mesh or anything like that. It was just that the assumptions that we made originally weren't correct. And of course, once we looked into this further and actually analyzed the tank with all three sides in here, all the other three sides in here with the approximate pressure load, which is what would happen in the real world, we then found that in reality, with all of those walls properly loaded, the deflection really should be more like 0.08 inches, which, if you were trying to run a simplified single wall case, turns out to be very close to assuming the sides of the walls were fixed and not hinged. So basically, we were able to figure out not only what the true displacement should be in the software by realizing that the hand calculation was making a different assumption. We also realized that if we wanted to continue using that hand calculation, it would be better to use a different formula that assumed the edges were fixed and not simply supported. So again, it's always important to ask yourself what the assumptions of any kind of simulation or calculation method are, and make sure that they match apples to apples. Of course, there's lots of other things that could cause a discrepancy in results between your simulation and something else. Another important thing to consider if you're trying to match a real-world test, for example, an experiment, a physical test, is, first of all, was it an experiment under controlled conditions, or are you trying to set up a simulation to mimic the real-world usage of a product? You've probably all seen how maybe in stores or on a commercial, furniture or maybe footwear manufacturers will have an apparatus to show that something is being repeatedly loaded or impacted and that it can withstand a blow 2 million times. Well, is that going to be exactly the same as the loading conditions for when someone's sitting on that couch or someone's wearing the shoe? Probably not. So you should ask yourself what thing you're trying to simulate, or what are you trying to match in the conditions that you're putting in to your simulation. It's always helpful if you have some explanation of the experiment setup, if that's what you're trying to compare to, so that you know that the proper materials have been defined in SOLIDWORKS. And this goes back to a point that Glenn made on Tuesday, which is that even though the built-in SOLIDWORKS material library is really handy, you should always make sure that the properties that you're assuming are the same as what you've been given, which, of course, you can get from your vendor or try to validate from a number of other sources what material you're actually using. And, of course, also the realism in any restraints and fixtures and how the model might be attached to the rest of the framework or whatever it is a part of in the larger assembly is all accurate. Loading conditions, of course, are very important too. One of the main things you should ask yourself is, are you even running the correct study in the first place? Remember that the static analysis, which we've been talking about since last Tuesday, has a number of assumptions built right into it. For example, small deflections and the fact that the loading conditions are more or less constant. If your product is instead, being subjected to a shock load of some kind, that's a very different load than just a static load. And of course, ask yourself if there are other loads that might be having a significant impact besides just the main, let's say force or pressure that you've applied. Is friction important? Is gravity important? If it's a dynamic problem, you need to account for the damping. Remember, different types of physical conditions might require a different kind of simulation. And a lot of times we also get asked where error might be introduced into the simulation. Sometimes we are asked what the inherent error or accuracy of the program is. And that's honestly a tough question because it's kind of based on the misconception that there is inherent error to the program. And there isn't really any inherent error to, let's say, the calculations that the program does. If you see error between the results you're getting and what you would expect from, let's say, a hand calculation or real-world result, is typically related to differences in the geometry, whether you've maybe modeled it differently than the real model looks like, or perhaps if you simplified the geometry in a way that also kind of removed some detail that you needed. And of course, meshing can also introduce error, and that's the whole point of convergence, is to try to get that part of the error out of the equation. But it turns out that most of the error really comes from the setup, what we call the mathematical model. All of those assumptions we're making on the materials and how the model is supported or what the loading conditions are, that's where most of those discrepancies will typically come from. And really the inherent error to the program, which would really just be sort of the rounding error in the solver, is minimal. It's less than 1%, if anything. So you will not be able to pin the blame for error in the analysis just based on the fact that the solver itself caused it. It's always going to be due to the input conditions, whether we're talking about geometry or the loading conditions or the mesh. If you are looking for some more confidence in your results, if you want to validate that the software does give the proper solution for a particular problem, assuming all the conditions are right, we have a number of validation examples built into the software. There's an organization called NAFEMS, North American Finite Element Modeling Society, and they produce a series of standard validation examples which can be solved by hand and then also in an FEA program. And so these examples are available inside SOLIDWORKS Simulation under Help, SOLIDWORKS Simulation, Validation, and then the NAFEMS benchmarks. Also remember that if you're trying any of these situations where you're trying to get a realistic result that matches something in the real world, remember that golden rule, garbage in, garbage out. That's where those discrepancies are going to come from. And also keep in mind that sometimes it may not really be worth your time to check all of the input conditions to make sure that they exactly match the real world conditions. Again, we all know that, of course, if you're, for example, using a 1060 aluminum alloy, we can pick that material right from the database. And if you want to verify that the material conditions that you're actually using in the real product are exactly the same, you may need to do some extra work to go check with the vendor and make sure that there aren't any slight differences there. If you'd like to save that time, then it's perfectly fine to just assume that your part is made with slightly different material and basically ignore the whole question of whether the simulation matches the real world. If you can accept that there might be some level of error due to differences in the setup, you can still get a lot of value out of your simulation by comparing the results of different designs in the software. After all, that's the main reason why the simulation tools are built into SOLIDWORKS, your design program, so that you can try out all of these different design options very quickly and figure out which one is the best. You may not know within 3% what that stress is really going to be in the real world, but you will know that you made the right choice when you were trying to decide, for example, what gauge of sheet metal to use, or if you needed to add some stiffening brackets. Okay, so now that we've covered those aspects of how to make sure your simulation is accurate and gives good results, let's switch gears and talk about SOLIDWORKS Flow Simulation, which is totally separate from the linear static stress analysis that we've been talking about up to this point, both on Tuesday and today. So flow simulation, of course, isn't used as often as the stress analysis, so some people may not have as much familiarity with it, but just to recap the basics, SOLIDWORKS Flow Simulation is the embedded CFD, which means Computational Fluid Dynamics, analysis tool inside SOLIDWORKS. It's useful for evaluating any product that you might design for things like optimal flow rates or flow paths, proper temperature requirements, optimizing aerodynamics, velocity profiles, and these types of things are useful in a number of applications, everything from piping systems, pipe diameters, and tube bend radii, estimating electronics cooling performance, whether fans or heat sinks are going to do their job, heat exchangers, whether heat can be properly transferred between, for example, the air and a liquid cooling solution. Also in transportation conditions, and everything from aerodynamics, automotive, and a number of those. So the general procedure of flow simulation, at least conceptually, is pretty similar to a stress analysis. We're going to still take the geometry we have from SOLIDWORKS, pretty much any model we want, whether it was built in SOLIDWORKS or even imported. And the only real difference here is that most of the time for flow simulation, you're going to start the analysis with a wizard interface we have, which will take you through most of the basic setup steps that you need. And once that wizard's done and we've defined all the main parameters of the analysis, we'll be able to go in and specify the specific conditions, except instead of things like forces or fixtures, we're going to be specifying conditions like the material properties and heat source values, boundary conditions, which govern what the flow is doing in the analysis. And then, similar to the stress analysis, we'll figure out what the results are that are important to us when we run the analysis, and then we'll have some results that we can evaluate, and similarly, have a discussion about what the results really are telling us, if they're indicating some sort of a failure, if they are telling us that the design should be changed, and if the results are accurate. So as far as the geometry preparation in flow simulation, first of all, I just want to mention that similar to the stress analysis, it's usually a smart idea to do some simplification, especially if you've got a large assembly with a lot of small components, like, for example, transistors on a circuit board and things like that. You may not need all of that geometry detailed in the analysis. It may not have a significant effect on the airflow, for example. So usually there are some simplifications you can make, suppressing parts or getting rid of features that may not be important. And then the other thing we need to consider when we're setting up a fluid simulation is whether we want to do an internal or external analysis. An internal analysis means we're going to be evaluating what happens to the liquid or gas or whatever it is on the inside of a model of some sort, an enclosure for electronics or a piping system, whereas external would just assume that the fluid's around the outside of the model. Again, similar to an aerodynamics problem or some sort of a projectile in motion, something like that. And of course, you can do a combination of the two. You would also be able to do an external analysis and evaluate the inside of a box or enclosure of some kind too. So let's look at a common example that we see pretty frequently in customers that need to use flow simulation. Here we've got basically a simple kind of thin format computer, possibly mounted to the back of an HDTV or something like that. And so we want to evaluate this to make sure that the chip in this box isn't going to get too hot and exceed its design requirement. So again, this is the assembly more or less how we would have it in SOLIDWORKS. Maybe we've done a little bit of simplification to get rid of some parts that may not be important. And so once we think we've got the geometry the way we want it, we can jump into the wizard and we'll be able to choose things like that internal or external setting and then see if we can proceed with the setup of the analysis. So in Flow Simulation here, which I can access just by going to Tools and then Add-ins inside SOLIDWORKS. Of course, it's a checkbox just like any other add-in that we have. The Flow Simulation tab in the Command Manager will be available, and we'll start by hitting the wizard button. So I'm going to give my project a name here. We'll call this Baseline Vent Design. And I'm using the default configuration here where you can see I've got these 3 vents in the back of the enclosure. Of course, you can pick other configurations, which is a common procedure for flow simulation if you're trying to figure out which version of a design is the best for, let's say, cooling or just general flow properties. So I might, for example, run this first analysis on the default design and then try another vent pattern later and compare the two. So once we've picked the version of the model and we've named the project, we need to pick some units here. You can choose from default unit systems or customize them if you'd like. For example, I probably want my temperature in Celsius here if that's the requirement that I've been given. And then at the third tab here in the wizard, we have to make some main decisions about the scope of the simulation we want to run. Where do we want to assume the fluid is? Is this an internal or external problem? And what physical features do we need to be included in the calculation? So for example, here I probably are mainly just concerned about the airflow inside the box and not really what's happening around the outside. Although if this was going to be placed in a particular position, let's say like in an enclosure rack, then maybe I would need to account for that external airflow around the box as well. And I could do that while also seeing what happens inside the box. But to make the simulation a little simpler and faster to run, I'm going to choose internal in this case. As far as these physical features go, if I want to know what the temperature in that chip is going to be, I need to make sure to check this heat conduction in solids box, which will automatically do all of the thermal calculations both inside the solid material and between any of these parts and the fluid that surrounds them. So it's not necessary to export any of this to another thermal study later. All the thermal calculations will be done in conjunction with the fluid calculations. In fact, if radiative heat transfer is also a concern, for example, if we're talking about very high temperatures or it was a product that would be sitting out in the sun all day, I would be able to turn on radiative heat transfer as well and account for that so that we have all 3 modes of heat transfer available. We also would be able to turn on gravity, which in this particular case is probably important if I want to see the hotter air rising to the top of the box. So I just need to make sure to put it in the correct direction here. And I also could run this simulation as a time-dependent problem if I wanted to see how long it takes for the box to heat up from, for example, the normal room temperature. Otherwise, if I don't check that box, this is going to be what we call a steady-state solution, where it'll just show me the temperatures in all of these components and what the airflow looks like after a long period of running at the same conditions and same flow rates. Here we need to also pick the fluid now. So this is going to be air, but also just notice in flow simulation that we have a lot of other options, whether we're talking about gases of some kind or liquids. For example, I could add water to this simulation as well if I had a water cooling system that I needed to simulate inside the box as well. And mixing of fluids is also permitted as long as they're the same kind of fluid, gases and gases together, for example. You'll also notice down here that it says flow type laminar and turbulent, which means that flow simulation is going to figure out for us if the flow is laminar or turbulent and not force us to assume one or the other, which is a limitation in some other CFD programs on the market. So that takes the guesswork out of those aspects of boundary layer formation and the like. We also need to pick a default solid material since all of these components need to have a solid. And typically you'd want to pick whatever the most common material is. For example, you might pick silicon if a lot of chips on the board were made of that material. And then we also can specify some wall conditions. Here we can choose what happens at the outer walls of this box. If we want to assume that there is some heat loss to the environment, for example, we can put in a known heat transfer coefficient or a known wall temperature on the outside of the box. Or we could leave it at the default assumption of adiabatic. We can also pick what our initial and ambient conditions for the simulation are. For example, if this is going to be running in an optimal environment, maybe a nice air-conditioned room, we can leave it at sea level temperature and pressure. But if this is supposed to operate, let's say, in the desert or at the top of a mountain, then of course we can change those conditions to be more realistic. Finally, the last part of the wizard here is what we call the result resolution. And this is where we can pick essentially the accuracy of the problem that we would like. By pushing this slider that we see here higher to values above 3, that will basically refine the mesh and use more stringent accuracy checks in the simulation to give a more accurate result, which will of course also take longer as far as the calculation time. You have some basic options here for how much detail the mesh should try to capture, whether we're talking about the thickness of a thin part or the gap, for example, between heatsink fins. And you also would be able to control this mesh more manually if you needed to, but typically in flow simulation, the automatic settings are a very easy way to get good accuracy without a lot of work. So finally, when we're done with the wizard now, we can proceed to the rest of the setup of our simulation, but we're getting a message here which says flow simulation has fluid volume recognition has failed because the model currently is not watertight. And you might look at this and say, well, watertight is a dumb word because we picked air. But it's just telling us that because this is an internal simulation, the box needs to be fully closed off so that the program can figure out where the fluid is and where the outside of the box is. So of course, we have these vents here, and we're going to need to fill those in. And the other reason for that is so that we can apply the flow conditions to those openings too. We need to tell the simulation if air is coming in through those vents, or if we don't know that, maybe what the pressure is. So we have an option here to click yes and go to the Create Lids tool, which can automatically fill those gaps in for us. So I'll click yes, and the Create Lids tool pops open here, and it allows me to simply click on a flat face of a model, and then it will create some extruded bodies to fill those in. If you have another more complex opening, or maybe a curved face, you can also just create these lids manually using whatever features you like. So now that the vents have been filled in, I'll have a place to pick my conditions, but I'm still getting a message here that says the model is not watertight after I update the mesh settings. So in this case, that means I must have some other gap somewhere in the model. So I don't want to do the lids tool again, since I know I've already created the lids that I need, and instead I just want to try to figure out where that other gap might be. So let's click no to this message. You can see again it's warning us that we have a non-watertight model still. And so if you ever encounter this issue in flow simulation, the best thing you can do is use a tool we have called the Leak Tracker, which has been improved for 2014. It's under Flow Simulation, Tools, Leak Tracking. And this will automatically figure out where the gaps in that enclosure are. All I need to do is pick a face on the inside of the model somewhere. So let's click on this face in the back side of the enclosure. And then we'll click on the face on the outside as well, let's say on the front over here. And we simply click this Find Connection option, and the red path will be drawn on the screen for us, which traces where the airflow would be escaping from inside to outside. And we can see where it's progressing here right through a gap in the bottom left of the enclosure. So it turns out because I used sheet metal features to create this enclosure, and I didn't put any kind of corner weld or any closed corner or anything like that, I've got this gap here which is causing the issue. So of course I just need to modify the geometry to correct that, and in this case I've already done so, so I'll go ahead and switch to the corrected version of this enclosure part. that I have right here. Simply click on it, and in this new drop-down for 2014, I can click the fixed version of that enclosure. So now that I've corrected that geometry, you can see the non-watertight message has gone away, and I can also verify that I've set up the model correctly by using the Check Geometry tool. This will allow us to go in and calculate what the fluid and solid volumes are in this model, and also show the fluid volume on the screen just to confirm that the fluid region is the same shape and same size that we expected it to be. So now that we know we've set up our geometry properly, we can proceed to the rest of the setup of our flow simulation project. Typically, the first thing you do after the wizard is complete is to set up what we call the boundary conditions. These boundary conditions define what the fluid is doing, and they're mainly important for internal analyses where you have those openings in your box or piping system. So they define where the fluid enters or leaves that model, and there are two main kinds. There are flow openings where we know the inlet or outlet condition of the fluid, and there are pressure openings where we don't really know if the fluid's going in or out. Or maybe we do know that it's an inlet, but we don't know how fast it's going or what the flow rates are. So we have to pick one of these two main options for all the boundary conditions, and then flow simulation will calculate the rest of the unknowns for us. So if it's a flow opening, that's great, but if it's a pressure opening, it will find out what the flow rate is automatically. So in this case, we probably don't know what the flow rates through all those vents are, and that might be what we're looking for. Now, the main thing to remember when you're trying to create these lids and create these boundary conditions is that they must always be applied to the inside face of those lids that we already added to the model. The inside face is where the fluid is touching the lid, so that's why it has to be selected like that. We can, of course, go to this drop-down menu and click Boundary Condition, and we can select the inside faces of these lids and then pick what kind of condition we want to assume. Again, we don't know the flow rates of these vents at the moment because these are just open to the environment. So instead, we're going to use the pressure opening condition, and we'll just assume that we know the pressure on the outside of the box at these openings and also what the temperature would be if air happens to be coming in through these vents, which it probably will be. Again, you can tell by the icon that we're assuming a pressure but not any particular flow parameters. It could be going in or out. On the other end of the box, we have a fan here, and one way to simulate that fan would be to do another boundary condition where we know that it's an outlet fan, and we perhaps might know the volume flow rate of that fan. So we could click the face that represents where the fan blades are and plug in that value. Now there's also another way we'd be able to account for this fan, which I'll get to in a few moments. So for right now, I'm going to delete that boundary condition. Typically, the next thing that you need to specify, especially if you're considering heat transfer, are the materials and heat sources in any of these simulations. And again, the heat transfer is usually important for electronics cooling problems, although, again, if you're designing a heat exchanger or certain kinds of external aerodynamic problems, heat transfer might also be important there. Now, when you're defining the materials, that, of course, is going to include thermal properties like the conductivity of the material and specific heat. And because the properties are a bit different than what you need for a stress analysis, that also means the library for flow simulation is going to be different than SOLIDWORKS material library or the SOLIDWORKS simulation library. So just keep that in mind. There are also a number of ways to define heat sources in the simulations. We'll be able to just manually define a certain heat power, for example, in watts or other units. We'd also be able to use something called two-resistor component model, which is common for PCB components that you may have a spec for from the manufacturer. We can also define things like perforated plates over the fans or vents in a box, printed circuit boards that are defined by the layers in the board and the coverage of the traces. And of course, all of these things will typically need the thermal properties associated with them. And some of those conditions are more advanced that are available in what we call an electronics cooling add-on for flow simulation, which is a special package with extra capabilities specifically for this kind of a problem. So for example, in this simulation, anything that's not the default material of silicon, I would want to go in and define as a different material. So I could go to solid material, pick the heat sink, and for example, pick aluminum. It is also possible to import the solid materials from the model that you've created by right-clicking solid materials and picking import data from model. And that will basically figure out what the material was that you've applied to each part and try to find the comparable material in the flow simulation engineering database. Now, in some cases, you may want a solution that takes a little bit less time to set up all these materials and heat sources, and typically in circuit board applications. So an important enhancement for you to be aware of is that in 2014, we can now import a lot of these properties directly from SircuitWorks, which is the add-in for SolidWorks that can translate an ECAD board file into the 3D model using the library of board components. So all those values like the heat source, the conductivity of the material, and the specific heats, and all of those printed circuit board properties, they can be imported directly into the setup conditions of flow simulation. And it's also very useful if you plan to go back and forth between SolidWorks Flow Simulation and your ECAD design tool, where you'll be re-importing the model multiple times, which will save you a lot of setup condition time. Okay, once all of the input conditions, like, for example, boundary conditions, heat sources, and so forth are set up, another one being fans, which, by the way, is a more accurate way to simulate the performance of a real fan by picking the actual manufacturer's number, product number. So here we've got, for example, a PAPS 405 fan. You just pick if it's an inlet or outlet. Once we do all that, then we can go ahead and set up what we call the goals for our simulation. So what are the goals? Well, the goals are basically the key parameters that you're most concerned about in your simulation. What are the key results you want to know? If you were running a stress analysis or some other kind of simulation, they're typically called sensors in there. So slightly different name, slightly different purpose. In addition to making it easy to check the key values from your simulation, they also ensure a certain level of accuracy in the solver for flow simulation. So there's, again, this word convergence. Although in flow simulation, when we talk about convergence, we usually mean something different than mesh convergence, like in the stress analysis. In flow simulation, the way the solver works is to typically start out the solution of the problem as if it was time-dependent and a transient problem until it finds what the steady-state solution is once everything's settled down. And that process is called convergence. And it can typically be a lot of work in other programs. But in flow simulation, by specifying what these goals are, the key measurements you're looking for, that will ensure that the convergence process goes smoothly and that you get accurate results for the steady-state solution for these problems. Also, when you run the analysis, quick note here, you can also run that simulation not just on the local computer that you have, but on another machine on your network. And whether you use it, your own computer, or use that network computer, all of the available CPU cores will be used. So for example, I could hit run here. I have those options to choose which machine I want to run it on and how many cores I want to use. By default, all of them. Although I could reduce that if I want to save some CPU power for other tasks. And then, of course, I could start the simulation, and the mesh will proceed. And I'd also be able to track the values of those goals that I set up while the simulation is still progressing, which can be a great tool to stop the analysis early if you don't think something looks right and you think you need to make some changes to the setup. So, of course, some initial geometry prep and rebuilding of the model will take place, the mesh will be generated, and the solution will start. And typically, for these types of flow simulation problems, you won't need a lot more hardware than you have for the stress analysis tool. The laptop, in fact, that I'm using right now to run the simulation is the same specs as what Glenn was previously using for the stress analysis tool. So of course we can see some initial results here. We've got some data on how big the mesh is, how many cells there are, which is the equivalent to elements. And we'd be able to track, for example, a cut plot or some other things that as far as what's happening inside the simulation. So let's kill this and go ahead and preview the final results I've got, which in this case would have taken about 20 minutes or so. So just to recap the setup conditions, we've got most of our materials as that silicon material, and then some of the parts are aluminum, like the heat sinks, and of course we've got some plastic components like the fan and so on and so forth. We've got those environment pressure conditions defined at the vents to allow air to come in at whatever rate it should end up coming in due to the fan, which is at the other end here. And we've defined this fan as an axial normal computer fan from, in this case, Sanyo Denki, which, by the way, includes the proper fan curve so that we can see at different pressures what the fan's true flow rate might actually be, which is more accurate than just assuming the number ourselves and typing it in. And also in this case, the circuit board was defined by a number of layers here. In this case, it's a 2S2P board, and we could type in exactly what those layer thicknesses are, and of course, all of the material properties for the layers, if it was copper and FR4, for example, the dielectric. And we've also defined this 2-resistor component condition for the CPU, where we assumed that it was outputting 15 watts of heat, and again also had the appropriate junction to case and junction to board inductance values. The goals for this particular simulation that we were concerned with are mainly the CPU temperature. That's the main design requirement we have. So here we've got a volume goal, which is measuring the maximum temperature in the entire part that we've modeled for the CPU. We've also got a volume flow rate goal to figure out exactly how much air that fan is pushing, and also what we call a global goal to figure out what the bulk average temperature of the air is inside the box. And this is also a common question we get sometimes, which is what's the difference between average value and bulk average value? And the answer is bulk average value is weighted for the mass flow rate. So typically if you're trying to compare the measurement of, let's say, a temperature in a fluid as it's passing through somewhere, the bulk average will probably be closer to the measurement you would get if you had some sort of a probe in the middle of that flow stream and not towards the side. So here we can look at our results. And when you're interpreting results in flow simulation, a good workflow typically is to first go right to those goals that you created, since those are the main parameters you're most interested in, and check if the requirements you have in your design were met. So was the maximum CPU temperature exceeded, or does your piping system have a low enough pressure drop to prevent resistance or back pressure? Then once you've checked that, maybe you've determined that the design meets all the requirements, or maybe you've determined that it fails some requirement, or maybe that it's really over-designed. You can try to figure out from the other visual plots you have, such as cut plots or flow trajectories, why or how the design should be modified. So for example, in our CPU box here, we can look at our goals and figure out that in this case, our CPU temperature is a bit high. It's a maximum temperature right now of about 81 C, and a typical requirement for something like this would probably be more like 70 Celsius. And we can also see that our flow rate was about 4.4 CFM, whereas the maximum flow rate for that fan was 6 CFM. So it turns out that the fan isn't actually performing up to its max specifications because of the pressures in the box. And we've also figured out that the average temperature in the box here is about 25 C, pretty much room temperature. So the overall problem doesn't really seem to be heat buildup in the box. It looks like primarily the heat sink on the CPU itself is what needs to be improved. And of course, by looking at these other visual plots, for example, a cut plot, which can show you all of these temperature or pressure or velocity results on a plane inside the model, these are where you can help figure out what sorts of design changes are needed. For example, here we can see that we do have pretty velocities coming out of the box near the fan, but there are some stall regions right around the heatsink and above that circuit board at the top. So maybe the fan isn't optimally placed at the moment. We can, of course, also look at things like temperature and figure out where heat buildup is. Of course, it is right around that CPU and where the heatsink is. So maybe we need a stronger fan and more of them, or maybe we need some vents right by that CPU. We can plot the properties of the flow simulation in flow trajectories as well, which are basically 3D streamlines inside the fluid domain. So here we can see, coming from the fan, for example, where exactly those streamlines would go. What would the fluid look like going from the vents out of the box through the fan? And it will trace it through 3D space and also allow us to plot almost any parameter we want on these trajectories. For example, here I'm looking at velocity, so I can clearly see that I've got a very large recirculation region here where I've basically got dead air. And I could also look and see from the temperature plots where that hot air is building up. And really the problem again seems to be not that I've got heat buildup, but that it just can't cool that CPU well enough. So maybe I need a better heatsink design, or I need a better fan. And of course, all these things can be animated. So of course, if you want to learn more about flow simulation, both the setup and the recommended procedures for ensuring good results, or if you're just looking for more information on stress analysis or really anything else we've talked about in this Simulation Night School, we do have some online training offerings that you may not be familiar with. We've actually expanded them recently, and we offer 8 simulation courses online now via GoToMeeting. If you want more information on those, you can go to hawkridgesys.com/training, and I'll show you all the offerings that we have and the content and curriculum, and of course have a link to sign up. Of course, you always are going to have access to the Hawkridge Systems support team. So if you have any questions about simulation in general, for example, you're going to set up a new stress analysis and you can't remember what that one option inside the force condition does, or you can't remember what this contact condition will do, give them a call. They'll be able to clarify that for you with no problem. Or, of course, you can email them at support@hawkridgesys.com and also do GoToMeeting if you need to show them something on the screen. You also can, of course, go to hawkridgesys.com and you can take a look at our knowledge base if you want to log in to the support forums there. You can also check out the series of videos that we have posted on the website under all the different product categories. We're adding a lot of new blog and YouTube content every day at Hawkridge, so go ahead and search for our YouTube channel as well. There's a link to it on the website, and you can see tips from everything to simulation, CamWorks, SolidWorks, Composer, almost everything you can imagine. And of course, we also have recordings of all of our different webinars, whether it's our normal e-learnings on Wednesdays that we do, or, for example, this Simulation Night School. It will be available soon at hawkridgesys.com, and you'll get a link about that in your follow-up email. That's all we have for you for 2014 Simulation Night School, so thanks again for joining us. If you have any questions related to anything we've talked about today or any of the content from Tuesday as well, Glenn and myself will be answering those through the question interface here. Otherwise, again, thanks for attending and have a good rest of the week.